Okay, I think we'll go ahead and get started. Thanks everyone for coming today. It's a pleasure to welcome you back. As always, I want to start with thanks to the Global Institute for Water Security and the Global Water Futures Project for underwriting this seminar series. And today I have the real pleasure of introducing Scott Tyler from the Department of Geologic Sciences and Engineering at the University of Nevada, Reno. Scott is an international thought leader in hydrology, and with a background or undergrad degree, I guess, in mechanical engineering before he moved into hydrology. Really, I think what is at the core of Scott's work is an interest in environmental fluids, and this has taken him in many areas. He's done a lot of work in vadose zone hydrology and hydrogeology, moving into imaging, glaciology, as you'll hear today, and the use of the DTS technology that you'll hear about as well. Scott serves as director of the Center for Transformative Environmental Monitoring Systems, and he's a foundation professor at Nevada, Reno. He also does a lot of community service. He's been chairman of the board of COASI, this consortium of universities that we are a part of here at the U of S. He's been chairman of the hydrogeology division of GSA, the Geological Society of America. He served as editor of Water Resources Research, our flagship journal, from 2005 to 2009. And I could go on. For this, he's received a lot of recognition. He's a fellow of the AGU. He's a recipient of the John Hemm Award for Excellence in Science and Engineering from the National Groundwater Association. He's won several awards with the Geological Society of America. He's a fellow of the Soil Science Society of America, fellow of GSA, and was a Darcy lecturer back in 1999, I think it was. It's really a delight to have Scott with us. I'm most appreciative of Scott being president-elect of the hydrology section of AGU, something that he'll begin in a little over a year's time. So it's terrific to be able to hand off the reins to someone I respect so much. So Scott, please.
Well, thank you, and thank you, Jeff, very much for that very kind introduction. I really appreciate it. And I also want to thank the Global Institute for Water Security for inviting me up here. It's a pleasure to be here. I haven't been to Saskatoon, I don't know, since about 30 years, so it's very nice to be here. And it's snowing at my home as well, so I'm in good company. So today's talk, even though I know this is about hydrology, we're going to talk about cryosphere, a little bit of frozen world, but my goal here is to kind of get you guys excited about the opportunities that we have for measuring things in environmental sciences. And again, as Jeff said, kind of my interest is in environmental fluid mechanics, so I don't care if it's water, air, or ice, but I am mostly a hydrologist by training. So as I talk through this talk, there's going to be some aspects of glaciology, are there any glaciologists in the room? Thank God. Okay. There's a sort of a waving question. So I may make a few faux pas because I'm not really a glaciologist. I just pretend to be. Very good. Okay. And everyone can hear okay, and you can see well enough? Everyone's good? Very good. Excellent. All right. So I don't think I have to tell this group, although occasionally I do have to tell groups, that the Earth's temperature is indeed warming. And as you can see on this graph, this is just a measure of temperature perturbations over the last roughly 160 years, 150 years, and indeed things are warming up. I talk to a lot of groups, some of them non-scientists, and sometimes this then begins, at least in the United States, generates this rather excitement about, well, climate change, we don't believe in it, well, forget it, it's happening. Whose fault it is, I'm not going to debate at this moment. We don't need to get into that. But indeed, things are warming. And I'm an engineer, as Jeff said. And as an engineer, we like to fix things. We like to get ahead of the game and make sure that we can predict what's going to happen and make sure we don't get caught flat-footed. And so, indeed, if the climate is warming, there are things we need to deal with. And one of those things has to do with sea level rise. So here in Saskatoon, most of you probably don't worry too much about sea level rise. But how often is it that you've flown somewhere and either as you landed or as you took off, you saw the ocean? Show of hands, right? It's pretty much everybody, okay? So some of our most major infrastructure components are very close to the ocean and potentially impacted by sea level rise. And again, here in Saskatoon, you may not think, well, sea level rise isn't that big of a deal to me, but we live in a just-in-time economy. We, meaning the developed world. Everything we do requires a transportation system and a network to move our stuff around. The developing world, okay, we often think about places like Bangladesh and the Maldive Islands. They will be impacted by sea level rise, and indeed they will be significantly. But we often forget that we, as in the developed world, we will be very significantly impacted. If you think back to what happened during the tsunami that hit Japan a few years ago, you know, if any of you had Mazdas or Toyotas or Nissans, it was a little hard to get parts for a little while for those cars. Fortunately, those companies have diversified. But pretty much everything you buy today was made only a few weeks ago. Okay, that's the way the world works. And so if we can't move our transportation systems around easily because of sea level rise, we're in trouble. Okay? And so it's critical to everybody. There's another piece of infrastructure that I just want to mention, or I want you guys to think about. Other critical infrastructure that most big municipalities who are on the coast, which is where 70% of the world's population live, what's another big piece of infrastructure that's right by the coast besides ports and airplanes? Anybody have any other ideas? Any civil engineers in the crowd? Environmental engineers? Sewage treatment plants, exactly. Sewage treatment plants, have to run 365 days a year, 24 hours, 24/7, and they typically are at the lowest point in a watershed. Okay, the city of New York, Los Angeles, all these, their sewage treatment plants are basically at the coast. And you're not going to move those very easily. They're multi-billion-dollar facilities, and no one wants them in their backyard. Okay, where they are is where they're going to stay. So sea level rise, what are we going to do with our wastewater treatment facilities? We need to know, is sea level going to rise 6 inches? Sorry, 15 centimeters? I have to remember I'm north of the 49th parallel. Or is it going to rise 2 meters? Okay, these are important things. All right, so that's what we're interested in. This is a picture from LaGuardia Airport after the Sandy hurricane that came through in 2012. The airport was closed for a week. It's at sea level, essentially. And the estimated cost during that closure was on the order of $500 million. Okay, was the impact. So sea level rise is a big deal. What about sea level rise? So sea level is rising for a variety of reasons. I talked to some of the students today. Part of it is because the oceans are warming, so we get some expansion. And the other part is because we are melting glaciers. Okay? And one of the areas that is the most interesting and potentially most rapid place where we're going to melt glaciers is West Antarctica. And so sometimes you will hear this term, West Antarctic ice sheet collapse. Okay? And what does collapse mean? Well, in West Antarctica, we have ice shelves and we have ice sheets. The ice sheets are the parts that are grounded on land, and the ice shelves are the parts that floats. Most of the ice sheet, there we go, sorry, that should be sheet, not shelf there, is grounded below sea level. And why is that important? Okay? It has the potential for not necessarily collapse, but what I'll call runaway melting. And I'll talk a little bit in brief as to why that is, because I think the physics are kind of important here. This could lead to a sea level rise of a few meters in relatively short time. And I'm saying relatively short time, meaning some of you will be around when it happens. Could be around. Okay? I'm hoping to be around. Let's put it that way. Not sure I will be, but I'm hoping to be around. Okay? And what holds these things in? Well, it turns out that the shelf glaciers, the parts, and I'll show you in just a second, the parts of the glaciers that are actually floating, those are the corks that hold these big ice sheets in place. Okay? And these are the things that we just heard just a few months ago, this enormous ice shelf, this big iceberg that collapsed off, that came off of Antarctica called the Larsen C shelf. This is a huge floating, essentially becomes a tabular iceberg. Okay? Now, so what's going on? What's the weird thing that's going on here? And I'm going to have to move over to the screen, one of these screens. And you guys can see over here pretty well. Here's a simple map of what West Antarctica looks like. I'll show you a map of Antarctica in just a second. But let's just get one thing straight. That direction to your left is the South Pole. Okay? So what's weird about this big glacier? Here's the ice sheet. Here's the ice shelf. This is the floating part. The length scales, just to give you a sense, this length scale from the edge where the shelf hits the ocean to this grounding line, which is where the ice is grounded on the bottom, this can be as much as 500 kilometers. Okay, so this is a big distance. This depth might be a few kilometers. But the weird thing about West Antarctic is, notice how the continental shelf slopes backward toward the South Pole. Okay, this is a combination of two things. One is the weight of the ice, but that's relatively small. Turns out that West Antarctica is actually not land, it's ocean. Okay, and the ice sheets have coalesced over the top and formed glaciers over it. Okay, so these are called marine glaciers. We'll talk about the mechanisms for melting in just a little bit. Okay, so why does this thing collapse? And you'll hear the term again, collapse. Not necessarily a collapse. So the bed slopes back toward the South Pole. That gives access then to the grounding line, the base of the glacier, access for ocean water, which can be warm, to get to it and begin to melt. Okay, as that grounding line moves back, as it melts, I have less friction, so the glacier can start to surge. But the key aspect is, for these glaciers, is that if you noticed, let's go back to that picture quickly. Notice the shape of the glacier. It's kind of like this. Okay? So as it comes back like this, it turns out the velocity of ice, for a big glacier, the velocity of ice scales to the third power with the thickness. So if I move back a little bit, the ice is now thicker, it now squeezes out, okay, and pushes its way forward, which then floats a little more ice, which makes this part open to the ocean and a little thinner, and it squeezes out. So this whole glacier, the ice sheet, comes out somewhat like squeezing a tube of toothpaste. Okay, just comes out as we begin to erode this grounding line. This whole thing just eventually starts to float. Okay, and it's a big chunk of ice. Now, who cares if a floating ice shelf melts? Does it change sea level? The ice that's floating already, if it melts, does it change sea level? Trick question. Yeah, got it right. A little tiny bit, because the density of ice is a little different than fresh water, but it really does, or seawater. It doesn't change it too much. But it's this ice that's all up here, that's all above sea level. This is the part that raises sea level. Okay, so if that ends up in the ocean, that's going to raise sea level significantly. Okay, so again, once this retreat starts with that geometry, the retreat, the collapse, may be unstoppable. And I'd recommend, there's a couple of papers here that I told the students I would give them these, that are really great descriptions of this process, really clearly, much better than I can describe it here. Okay, so this is a picture from Hulby's paper. And again, here's what happens is, as this grounding line moves backward, the entire glacier squeezes out more, and it's a feedback process. And this whole thing then comes out and begins to float, and all of this ice raises sea level in a relatively short period of time. Okay, so just to give you a sense as to where we are, because Antarctica, it's often difficult to, I'll talk about West and East Antarctica, and sometimes that's a little tough because it's at the bottom of the Earth. Who knows where's East and West? But East Antarctica is over to your left, and West Antarctica is over to your right. Just for scale, there's the South Pole. Apparently, you guys do like your Rough Riders, from what I understand. I have heard that from others. Okay, so these ice shelves then that are holding back the ice sheets, this is just a map of showing the ice shelves, the existing ones that are there. There's two big ones, the Ross and the Rhone-Filchner. Here's West Antarctica. Most of this ice is grounded below sea level. Okay? Sorry, you guys aren't getting much attention over here. I'll come over here. Okay. Most of this is grounded, again, below sea level. There's also shelf glaciers out here, the Getz, the Abbotts, and a few others here. These are actually where things are really melting. Okay, but these are enormous. This is like 500-600 kilometers, and they're buttressing and holding in the rest of this ice. Okay, and just to give you a length scale, this is what it looks like when those ice shelves intersect with the sea ice. So this is now early in the springtime, so there's still sea ice. This is glacier ice that's coming out, floating. Okay, so again, how do these things melt? Okay, there's three modes of heat transfer that begin to melt these ice shelves, that are always melting the ice shelves. We have a really interesting one, which is driven by the formation of sea ice, which causes a deep circulation beneath these ice shelves that goes as deep as 500-kilometer circulation cells. We talked about those in class. Those are really neat, but they melt maybe a meter a year. They're pretty slow. What's really driving the melting and the more accelerated melting today that we see is this circumpolar deep water. This is quite warm water, plus 2, 3 degrees C. And we're seeing more of that water being pushed underneath the ice shelves, probably due to changes in wind pattern around the Antarctic. This is what's melting that. And then we also can push a little bit of warm surface water off the surface underneath the ice shelf. And that's actually, for the data that I'm going to show you, that's what we're going to see. So here's just an example. Now we're looking down on one of these ice shelves. This is the Pine Island Glacier, and this is an enormous ice shelf. And just to give you a sense of scale, there's a crack in the ice, and it's, I think it's about 50 kilometers, 60 kilometers long. Moose Jaw is about 100 kilometers away, I think, maybe a little further. This crack, by the way, this was interesting. The U.S. was, the Americans had a base here. We were trying to drill through this ice shelf, and fortunately, they're on the upstream side of the crack. They didn't know about it. Then this was flown right before they were about to go out to the field site, and sure enough, half of our field site is floating away. Okay, so I'm interested in monitoring what's going on underneath these ice shelves. How do we monitor how fast they're melting, and what are the processes? Okay, it's a challenging place to monitor. Okay, try to get underneath them. Again, length scales of 500 kilometers, depths of multiple kilometers underwater. Anything we put through the ice shelf is irretrievable. It's going to freeze in, so there's nothing we can get back out of it, so it's hard to recalibrate. How do you keep things powered down there? The sun goes down for 6 months. How do you keep electricity going? And what are the variables that people are interested in? The oceanographers, this was my first interaction with oceanographers, and they're interested in a couple things. They're interested in temperature, T. They're interested in conductivity, because ocean salinity varies slightly, so they're quite interested in the salinity, depth, and then currents, velocity, horizontal velocities. Okay, we're going to just measure temperature mostly today, but we'll talk about other stuff. So here's what we did. A couple years ago, we were funded by the National Science Foundation to go out and drill through one of these ice shelves. And this is just a schematic of what things look like. We're going to drill a hole through there in the ice shelf, and we're going to install instrumentation and see if we can get it to monitor temperature and other things through this ice shelf and into the ocean below. Okay, at a place called Windless Bight. This was a collaborative effort with colleagues from New York University, Dave Holland and his students, who's an oceanographer, and Viktor Zagorodnov from Ohio State, who's a glaciologist. So it was a really neat, unique opportunity to work with, there were 3 of us who did water, sort of all different phases and chemistries of water. We all could work together quite well. It's quite fun. All right, so what are we going to do? We're going to measure this with distributed temperature sensing. And what is distributed temperature sensing? I know some of you have heard of this. Can I just get a show of hands? A few have. Okay. So distributed temperature sensing. We're going to take us time out. We're going to go back and talk about instrumentation for a few minutes. Distributed temperature sensing is I'm measuring temperature by only looking at the changes in the optical properties of a fiber optic cable. Okay? My fiber optic serves as a thermometer, and I use a laser to light up that thermometer to energize it. And I can make temperature measurements this is a slightly old slide, every 12 centimeters, okay, every second, for as long as 30 kilometers. That's a lot of measurements, okay? And I can make that at resolutions now that go down to even lower than this, about 0.02 degrees centigrade. So I can really resolve small changes in temperature at very small length scales and high frequency. Okay, that's pretty cool. Okay, we all know how fiber optics work, optical fibers work. We all have that? I didn't think so. I didn't. Okay, the advantages of DTS, we'll go through how it works in just a second. It's cheap. Okay, fiber optics are used in telecommunications all the time, so we can grab tools from the telecom industry quite inexpensive. The cost of optical fiber ranges between 10 cents a meter to as much as $10 a meter. Once I put it out on the landscape or wherever I put it, I don't mess anything up. There's no disturbance of the environment. And again, I can cover large areas of the landscape, either vertically or horizontally with this. So I can begin to resolve temperature across the landscape at high spatial and temporal resolution. So I kind of liken this to, think about if I had a weather station someplace and I'm measuring temperature. I can measure temperature continuously, but I can only measure it in one place. If I fly a satellite or a remote sensing tool over that does temperature, I can measure temperature across the entire landscape, but only at one time. Okay? I want to do both. I want to get temperature everywhere and at all times. So if I take my fiber optic cable and string it all around this room and just lay it on the floor, lay it all over all of you, I can get a distribution of temperature continuously in time and space. And once you start doing that, you begin to learn things about processes. You really understand what's going on, or you can. Anyway, you see things you never saw before. Usually that's what most advances in science and engineering are. We see things that we didn't see before. Okay, we get the right microscope. Now, that's why we do it all the time, so we can hear you, we can listen to you all the time. All right, so how does an optical fiber work? Okay, this is a typical optical fiber. It's got a very fine, small, two kinds of glass, a core glass that's about somewhere between 9 and 60 microns in diameter, and over the top of that is a cladding glass, a different glass with a different refractive index. And then over the top of that is plastic and other things to protect it. Okay, so at the end of the day, our optical fiber is about 125 microns in diameter. That's a little bit bigger than a human hair. Okay, quite small. Okay, so how does an optical fiber work? Well, in simplest terms, okay, we consider optical fibers as light pipes. We pump a photon down through, here's a cross-section of an optical fiber. So I've just sliced it in half. Here it is in cross-section here. So here's the core glass, here's the cladding glass, a very simplistic view. If I shine some light into this core at the right angle, because of the difference in refractive index, that photon is going to bounce its way inside the core glass and stay there and make its way all the way to the other side. Okay, that other side could be as far as Japan. Okay, I could be transmitting a digital voice or image, those kinds of distances. So that's why we call them light pipes. They keep the photons in the core glass, okay? And there's very little energy or information lost. Sorry, okay. There we go. All right, so again, there's very little light loss. So what do? We send a short burst of laser light down an optical fiber, a very short burst, maybe 10 nanoseconds long. Most of that light keeps going. Okay, that's why I can use optical fibers to transmit lots of information without any signal loss. Off it goes. But there is a little bit of scattering that goes on, and when I point this laser at that sign here, and you guys can see that, what am I seeing? I'm seeing scattering. I'm seeing the light, the photons hitting the wall, being absorbed, and being re-emitted at the same energy. Okay? So as we send light down an optical fiber, once in a while, those photons will interact with the glass itself and scatter. Okay? Think of it like shining a flashlight in a dusty room. Okay? You see the specks of light, the specks of dust. Those are scattering events. It turns out that the color of those scattering events, if I could look very carefully, I'd actually see slight differences in color of the light coming back, because there are differences whether it's elastic scattering or inelastic, Raman scattering versus Rayleigh scattering. If I have Raman scattering, I actually will get some measure of the temperature. Okay, so here's just an example of how scattering works. So here's my light, here's my photon coming in, here's there we go. Here's an atom that the photon's going to interact with. That photon can be absorbed, it can send the photon out, and if in the simplest terms, think about it going continuously downstream. I won't see that. I can send one out, I can pop one out at a high angle, and that will go out through the glass and I'll never see it. But every once in a while, I get a scattering event that sends the photons back upstream, back from where I came. And that's the light I'm going to look for. That's the flashlight in the dusty room. Okay? The energies and the spectra of those returning photons tells me something about the temperature of that scattering site. And that's how I get temperature of it. Okay? And here's just a quick sketch of the frequencies that I shoot down. I shoot down wavelength at my incident light here at whatever wavelength this is, usually in the near infrared. And I get a variety of signals back, but I get two Raman signals back. Those are inelastic scatterings called the Stokes and anti-Stokes. One of those, the Stokes signal, which is a slightly longer wavelength light coming back, is relatively independent of temperature. The anti-Stokes, which is a shorter wavelength, a little bit more energetic, is strongly a function of temperature. Okay? So what I do is in the field is I pulse this light down the optical fiber. I watch to see it coming back, okay? Because I know the time of travel. I know the speed of light in the glass. So I send a little pulse of light. And it turns out in 10 nanoseconds, light goes about 2 meters. So I send a square wave 10 nanometers long, 10 nanoseconds long in length, goes about 2 meters. As soon as I send that pulse of light, I open some detectors, think of it like opening your eyes, and watch for 10 nanoseconds. So in 10 nanoseconds, light's gone 2 meters. So any light that goes out a meter and comes back 1 meter, that's traveled in those first 10 nanoseconds, that's light that I will see. I'll see the scattering, I'll see a pop of light, and I can tell what the temperature is of the first meter from that. I then close the detectors, I then open them again, and now I'm looking at the next 10 nanoseconds, and now I'm looking at light that's gone 4 meters. So out 2 meters, sorry for the camera guys, and back 2 meters. So now I get the light that's come from the next meter of fiber. And I keep doing that. I just keep waiting and opening and closing detectors until the light's gone all the way to the end of the fiber. So I now get a collection of photons back from the entire fiber that's telling me the temperature of the fiber. Okay? And again, it's because I know the speed of light in the optical fiber. I do that over and over again. The longer I integrate, the longer I do that, the better temperature resolution I get. We can go into those details later. So this is kind of how it works. In simplest terms, I have a box which sends out a pulse of laser light, goes down the optical fiber. I get some backscattered light. I measure that with a detector, and I tell you the temperature of the optical fiber. Okay? We didn't invent this in environmental sciences. I wish we did. I would not be visiting with you today if I invented this. I would be on my island somewhere in the Caribbean. But it's widely used in the oil and gas industry. In fact, where it really came to prominence was in the heavy oils, not tar. I know not to call it tar here in Canada. Not tar sands, it's oil sand. Okay, in the heavy oils of Alberta, and where they were doing steam-assisted gravity drainage, injecting steam. They wanted to know where the heat was going. It's in most of your high-tension electrical wires. So most big electrical cables have optical fibers spun inside them, okay, for measuring the temperature of an electrical transmission cable, which is quite useful because they're interested in looking for hot spots, places where the transmission cables may be overheating because of strain or failure. Okay, it's also used in most tunnels now in Western Europe to look for fire. It's a great fire detection tool. And so for us in environmental sensing, it's a great thing to do, great thing to use, okay? All right, so let's take a trip. We're going to go back to Antarctica. And again, the places we're interested in, the places of glaciers that may fail, are here in the West Antarctic. Again, most of the ice here in West Antarctica is grounded below sea level. Most of the ice in East Antarctica, certainly up here, is all your normal, above sea level, really thick ice sheets. Okay, there are some places in this part of Antarctica that are below sea level, but let's just worry about West Antarctica. So if we took the ice all away from Antarctica, melted it all off, the continent would look quite different. There'd be a continent here on the East Antarctic. There would be a few islands in West Antarctica. Okay, the rest is ocean. Okay, so we're going to fly down to the U.S. base, which is at McMurdo Station down on the Ross Ice Shelf. You fly down in a military aircraft from New Zealand. You land on the ice shelf. This is sea ice. You actually land on the ice, okay, with the aircraft. If you're lucky, All your gear is there. You come in, you hop onto a ski-equipped aircraft, and you go off to your field site. Okay, if you're unlucky, you go to Fort McMurray. Although I guess Fort McMurray is kind of a nice town. Yeah, it's okay. You go to the main base, and the main base looks a little bit like kind of a mining camp. This is in the summertime. There's about 1,200 people here at the main U.S. base. Great facilities, super people working there who will help scientists get their acts together. You go find your equipment, which you sent down months before. Not a good place for procrastinating scientists. You have to send your stuff, have to be ready a few months before. You find all your stuff, you put it on a vehicle, then you load it onto a sledge, and you motor out to your field site. Okay? We are motoring out to our field site. We're driving over about 200 meters of floating ice shelf at this point. There's about 1 kilometer of ocean underneath it. This was our camp where we're going to drill down through the ice. Okay? And again, we're sitting on 200 meters of ice. And active volcano in the background, but this is one of these big floating ice shelves, and we're going to drill through it. Okay, beautiful place. It was not any colder than here today. Conditions were actually quite good. This is a place called Windless Bight, which was nice, so it wasn't too windy, and we're essentially at sea level, so we're a couple hundred meters above sea level, so temperatures were reasonable. What did we do? Well, we first had to drill through this ice shelf, okay? And we drilled through using a traditional coring drilling rig. Okay, it's relatively small. You'll see a picture of it in just a second. We would retrieve 1 meter long cores as we went down. As we got close to the ice-ocean interface, this was an electrical drill. So electricity, seawater, they don't go together. Okay, they're not so good. So we had to actually melt our way through the last few meters of ice with a electrically heated melter. We'll talk about that in a second. We drilled a little over 190 meters. The problem with this was, so we drilled down with a core. Let's show you the drilling rig. This is the drilling rig. This rig has been used to drill in high altitudes in Peru and in Ecuador and also in Papua New Guinea. So it's really quite field portable. But we produced cores that were about, and here's the drill actually in operation. So just slowly make our way down. It took about 24 hours to make our way through that 190 meters of ice. And this is what an ice core looks like when it comes up. You can see the little, let's see, in this screen, can you see them well? I can see it well on my screen. The little dark spots on this are actually gas bubbles. So this is what people would use to analyze old atmosphere. So we would break these open, and they preserve the gas of what was in the snow and the ice as it compacted and finally sealed itself off. This was the diameter of the core that we drilled, except for the last little bit, which was about 50 millimeters in diameter, so about a little less than 2 inches in diameter. Everything that we had to go through that 190 meters worth of hole, including something that diameter. And the problem is the ice temperature. What do you think the ice temperature is? At the ice-ocean interface, what's the ice temperature? Freezing. Yeah, it's got to be a freezing point, okay? And the freezing point for ice for seawater at this salinity is about minus 1.9 degrees C. But further up in the ice column, in this floating ice shelf, temperatures are much colder because they reflect more the mean annual temperature of this region, which is about minus 20, minus 22 degrees C. So as soon as we hit the ocean, what's going to happen? We drill into the ocean, finally make our way in. This thing is all floating. So seawater is going to come up. It's going to come up to roughly about 30 meters below the surface. Remember that 90% of an iceberg is below the ocean, and so it's going to follow that hydrostatic rule, differences in density. But it's going to hit this ice that's minus 20 degrees C. It wants to freeze. Okay, so we figured we had of order 20, somewhere between 20 minutes and 200 minutes. Thank you, modelers. 20 minutes, 200 minutes. Which one do I know? Well, I'm not complaining. It was better than I could do. But we knew 20 minutes could be our shortest time. Everything had to go down the hole because it was going to freeze solid, or parts of the hole were going to freeze. Turned out we had of order 200 minutes, so that was just fine. But we still had to work kind of fast. Now, so again, sort of two things here. One is it's going to be small diameter, refreeze fast. But the other thing is, we didn't really know where the ice-ocean interface was. We kind of knew it, within about 5%. Well, 5% is at 200 meters, is 10 meters. And we could only melt our way through a few meters of ice. We had to be really close to the ice-ocean interface because our melter wasn't going to be able to keep the hole thawed out long enough to go very far. Long story, but no matter what, we needed to know where the ice-ocean interface was. How are we going to do that? Well, we got there and I said, well, how about this? We stop somewhere. We know what the ocean-ice interface temperature has to be. It has to be about minus 1.9. Let's stop drilling when we get within 10 or 15 meters. Lower this DTS, this fiber optic cable into the hole. Have lunch. Let the cable equilibrate to the temperature of the ice, and then measure that temperature and extrapolate where the minus 1.9 degrees C mark is. So here we are lowering it in, and I just want to show you, don't worry about the blue lines yet, let's just look at the red lines. So here's the temperature before we hit the ocean in that hole, and notice each one of these crosses represents a temperature measurement. I have a temperature measurement every meter on this cable, and it's pretty darn easy. Even me, I can extrapolate pretty well this curve to that minus 1.9 degrees C point where I have to hit the ocean. And it turns out, follow that dotted line, and right there is where we hit the ocean. You can see this is once we hit the ocean, we just dropped the cable in, and you can see the transition to temperature, to ocean temperature right there. So this DTS, because I was able to measure at very high spatial resolution, I can derive the gradient and I can use it to extrapolate. If I only had a thermistor chain with 10, even 10 temperature points on here and let it equilibrate, well, it's not nearly as good as that nice continuous measurement. So immediately, these tools give us insights into things that we couldn't measure before. Okay? Again, and temperature gradients can be a really important thing. Absolute temperature is nice. Temperature gradients tells us a ton about what's going on physically, what kind of heat transfer processes are happening. And if I recall, I asked the students, some of you are here in the class, I said, why is that temperature profile curved? Because if the ocean's at minus 1.9 and the land surface is at, let's say, minus 20, and I only have conductive heat transport, okay, we all know what conductive heat transport is, shouldn't it be a linear distribution of temperature? Okay. Now, the ice might be a little different at the top than at the bottom, and it is a little bit, but not much. So I'll leave you, we'll talk about, over a beer, you're going to tell me why that is. It's a good story. Okay, so at the end of the day, let's get to what we did. All right, so here's what we ended up with. We ended up with 2 moorings through this 200-meter ice shelf where we dropped our optical fiber down, and we're down at about 600 meters worth of ocean. So this cable is hanging at 600 meters. Below the ocean, and we're in the ice, and it's going to freeze itself in. We also put a few other instruments on the mooring for pressure, for independent temperature measurements, and a few other things. We drilled 2 holes. The first one, which just has the shallow cable on it, was just really to practice, to make sure we could do it. Got our techniques down, how fast we could lower the cable, and then we said, okay, let's make the other one. Okay, good. So let's see, what did we get? Let's look at some data. So this is a time and temperature and depth plot. So let me walk you through it a little bit. For a full year's worth of data, the bottom axis is time. And remember, we're in Antarctica, so January is the summer. That's their warm period. I'm measuring, this is just in the ocean. So the ice-ocean interface is right up there at the top of this plot. Colors represent temperature. All right? And what you can, and the big black bars are times when the instrument stopped working because of a variety of issues that had to do with electricity, and which we can get into later, which was a real learning experience. But as you can see, most of the world out there is blue. It's all at about minus 1.9. It's all close to the freezing point, except in sort of the late summer where you begin to see warm, and I guess that's warm here for Saskatoon, minus 1.5 degrees. That's warm here, right? Feels warm to me. Okay, where we see warm water coming in underneath the ice shelf, and this is the ice. This is the the warm water that's coming in off the Ross Sea that's slightly above freezing, and that's the water that's going to start melting this ice shelf. Okay? There's about almost 4 million data points in this. So again, every couple of hours we got a temperature measurement all the way down through the ice ocean, through the ice and then into the ocean. And what's neat to see, it's a little hard to see in this graph because we finished, this was a demonstration project, so we pulled our instruments out here. But if you look just right up here at the upper right-hand corner of this plot, you can begin to see warming water coming in, which is just repeating the annual cycle of this warm water coming in underneath the ice shelf. It's just beginning to come up here. Had we waited a little longer, we probably would have seen a repeat of this nice warm signal underneath. So what's going to happen? This is going to start melting the ice underneath us. And I'll just expand it a little. This is in the one summer, that first summer. You can begin to see, we had almost 100 meters of relatively warm water coming in under this ice shelf. And that's going to provide the energy to melt the shelf. Okay? This is with no downhole instruments. This is just with a fiber optic cable dangling in the water column. Okay, with a box up on the surface measuring. Okay, so just so you can see it a little bit better, I've just given you a couple of time slices of the ocean here rather than in color. And you can see the kind of light blue line is there in March. That was the warmest that the water got underneath the ice shelf, and at about minus 1.2 degrees C, okay? Which is going to melt ice, because remember, the freezing point's minus 1.9. Okay, very good. Okay, and this also gives you a sense, too. This is an important graph, because what about all these squiggles down here at the bottom, okay, down at 500 meters? I'll walk over to these guys so they see the same squiggles. Okay, I don't want to leave you alone over here. These squiggles. What are those squiggles? That's the instrument noise. Okay, that's the resolution. Down there, the water should be all at minus 1.9. There's not a lot of changes in circulation that should be going on down there. So that should be a constant temperature. And what you can begin to see then is, say, follow any one of these traces, the green one, for example, you can see that we had of order maybe 0.05 degrees swing in those measurements that should have been 0 swing. Okay, so that's telling us something about our temperature resolution. If you do the statistics down at that depth, we're able to resolve temperature differences of about 0.0, let's say 0.03 to be pessimistic, 0.03 degrees C, 330 millikelvin. That's pretty good from just a wire hanging in the water. At least I think it's good. Okay, sorry, you may not. You should. Trust me. All right, so here's what we were seeing, just so you guys get a sense of what's happening here, is that this is what we're here right at the edge of this shelf. Again, this is almost to scale. And we're seeing this surface water from the Ross Sea, which is slightly warm. That's the circulation pattern we're seeing. We're not deep enough here, and we're not at the right place to see this circumpolar deep water coming in. It doesn't occur at this particular location. But we are seeing melting. All right. Now, the big thing that what we're all interested in measuring is the melt rate at the bottom, or we call it basal melting. This is the critical factor for the stability of these ice shelves. Because if you think about it, if they're melting fairly quickly, as they get thinner, they're subjected to tidal fluctuations. They're going to do this, and they want to crack and break off. Okay, so that's what tends to form these big tabular icebergs. So the question is, well, I'm giving you temperatures in the ocean, I'm giving you temperatures in the ice, but I have this neat thermometer that's hanging in the ice, and the ice is now melting its way up my thermometer. Is there anything I can do to tell you how fast it's melting up? Okay, now important consideration with this instrument, or these measurements, is the box that I had on the surface could measure the temperature on my optical fiber every meter. So I would get a temperature integrated over roughly a meter. So meter, meter, meter. We expect the entire melt rate of the ice shelf here in a year's time to be a meter. Okay? So as my friend Kamini Singhal likes to say, this device, I'm kind of wearing beer goggles when I look at this melt rate, because the melt rate's going to be pretty small, and my ability to measure it is I have fuzzy glasses on. I really can't see it. Okay? But we have a sneaky system that we can do this. And this was a suggestion from one of my students, Scott Cobbs, who said, I have an idea. First off, we know what the temperature is at the ice-ocean interface. It has to be at the freezing point. Okay? If I assume the salinity at the ice-ocean interface is constant, which it's not quite, that's a bit of it's an assumption, but it's not bad, then I know what the temperature, wherever the ice and the ocean are, it's at the freezing point. It has to be. Okay, that's physics. Okay, so what if I start looking at the thermal gradient down at the ice-ocean interface as it changes in time? And I'm just going to show you quickly here. The right-hand graph, for all of you, is the thermal profile in the ice shelf, okay, from the land surface down to 200 meters or so. You can see where the ocean is. It's right there where the temperature goes vertical, because the ocean is much better mixed. Okay, up at the land surface, the temperatures change because we go through winter and summer, and the air temperature changes quite a bit. But in the ice shelf itself, there's very little change in temperature over time. This is from January 2012 to January 2013, no change. But if I blow up the gradient right down here at the bottom where it hits the ocean, now take a look. Here's 2012 in red, the one on the left. Okay, and just compare that with the black one, which is 2013. What you can see is that the temperature, the minus 1.9 temperature, okay, is much higher because the ice shelf has migrated up about a meter. Okay, and what's really neat is look at the gradient in the temperature in the last 4 or 5 measurements of the DTS through here. That's a straight line to me. Okay, that's pretty linear. So I can interpolate the gradient through this cable, and if I know that the ice-ocean interface has to be at minus 1.9, why don't I just take this slope, this line for every day, and calculate where is it going to intersect the minus 1.9 degrees C, roughly 1.9. It's a little bit different than that, but that's okay. Where is it going to intersect? And I can do that every day. And I can watch this thing move up. Okay? And indeed, that's what we did. So now we can calculate the melt rate every day. And this is a graph then over the entire time of the experiment, from summer, which is in January, to winter, back into summer. And what you can see is that when we first got there, the melt rate was about 1 millimeter per day. Okay, that interface was moving up at about 1 millimeter per day. That big warm chunk of water came in that we saw. The interface, and there's quite a bit of noise in the data, but we can fit a straight line to almost anything. And we got melt rates up around 8 millimeters a day. Okay, then what happened? That warm water pushed back because of other circulation things that are going on. The melt rate slows down to about 1 millimeter into the winter. The instrument dies for the winter. That's the big blank space in this. We turn it back on when the sun comes up. We have enough electricity. And the melt rate continues at about that same rate, at about 1 millimeter per day, till right at the end when we started to get that pulse of warm water coming back in seasonally again. Okay, and we didn't do any tricks here. There's no tricks of lining these up, so that gives me some confidence that it was melting at about 1 millimeter per day through the entire winter. The total melt rate is on the order of a little less than 1 meter at this site per year. So that's pretty cool. I was able to take an instrument that measures at 1 meter and begin to resolve things that are changing at millimeter scale. Not because I had great accuracy in temperature, because I had great accuracy in the thermal gradient. Okay? So when you're thinking about doing experiments, you always worry about temperature. Well, measure the gradient too. The gradient tells you a heck of a lot about what's going on in the system. Okay? Temperature gradients are critical. They tell you convective versus conduction heat transport. Okay, let's see if this works. Yeah, so this is just a graph. I'm just going to a little imagery here of the bottom. The bottom graph is the ocean temperature, and the top graph is what we call the draft, the thickness of the ice shelf as a function of time. And you can see that as we get that warm water, the ice shelf draft is decreasing. It's getting thinner. Okay, right through the warmest part, you can see we get most melt. And then as that warm pulse of water, that warm ocean water, is pushed back out as we get into winter, the ice draft stabilizes and doesn't change very much. Okay? So here's a simple way then that we can measure at daily scales the rate of basal melting with all of our instruments up on the surface, just with it optical fiber hanging down. Okay, so what are the next steps? Jeff, can you give me a time? I can't. All right, so we're going to call it quits. I've been talking to you long enough. I'm just give you a couple of other things that are going on. We can talk after the seminar. So right now we're moving to the place where is probably the most significant melting going on, which is a place called the Thwaites Glacier, which is over on that West Antarctic side. There's a major US and UK effort to go out and do a set of field campaigns there over the next 5 to 7 years, and we are involved with that to put in more of these moorings, more of these systems around through the ice shelf in various places. We can also do some really neat stuff with fiber optics that we can actually use the optical fiber as an acoustic sensor, as a geophone. And I'll leave that. If you have interest in that, come and talk to me afterwards. It's really quite amazing. We're using a little bit different kind of backscatter, but we can use the backscatter to estimate sound over a wide range of frequencies. And then finally, down in the Antarctic, you've all probably heard of Lake Vostok and some of these other subglacial lakes. These are lakes that are existing underneath the ice sheets. The question is, well, why are they there? It's a rather interesting question. And then what's going on? And so we participated in an exploration of the Whillans subglacial lake, a project called Wizard, where they actually drilled down. They got into the lake. They drilled down through. They lowered a probe to measure the heat flux out of the bottom of this subglacial lake, because the thought was maybe there's high heat flux there. That's why there's a lake there. The heat fluxes that were measured in the thermal probe that were stuck into the sediment were really high, about 10 times 10 times world average. And okay, one measurement, 10 times. Who's going to trust that? Well, I said, let's come back. We also installed an optical fiber into the hole that they used to drill down to this lake. That hole froze back in. The fiber froze into place, and we were able to then measure the temperature in the ice itself and calculate what was the thermal gradient in the ice above the lake. We know roughly what the thermal conductivity of ice is. We were able to then calculate what's the heat flux in the ice coming up above the subglacial lake. And it too was very high. It corroborated the measurement that was done in the sediment. Okay, so 2 corroborating pieces of information. So this is a wide open game. There's lots to do. Let's just skip through these for now. And I just want to show one last slide to close it off. So my colleague, John Selker, myself, and Drew Guswa, who's at Smith College back east in the US, we operate a National Science Foundation community user facility. And in the States, we have these facilities around the country where instrumentation is available to researchers from the National Science Foundation and other projects. Think of like telescopes, ships, high-precision GPSs. So we have these instrument centers around the US. We operate one for them for fiber optic sensing. So all the instrumentation that we used in the Antarctic is available. It's at very low cost to lease for research projects. And I would encourage any of you, if you're interested, if you have projects, think about, let us know. The best thing for most of you, because most of you are students, is we have a pilot program where if you're a young investigator or a student and have an idea on where to use this fiber optic sensing technique in the environment, write us a little 3-page proposal, tell us what you're going to do. You can have the stuff for free if we're not using it on other projects. And particularly, we have lots of extra instruments right now. So I would encourage you, now that you've seen what DTS can do, thinking about incorporating this into your research activities. Okay? And again, Canadians, it's fine for Canadians as well. We like our dear friends to the north. We have had a few issues with Canadian customs bringing things back in, so you might have to hand carry it back across the border. But what problems could that cause? I can't imagine any difficulties with that. All right, so that's the website. Go there, come and talk to me afterwards. With that, I think I'm going to call it quits and take any questions from you. Thank you very much.
All right, thanks, Scott, for a really fascinating story. Time for some questions. Yeah, Graham. Yeah, thanks. That's great.
Scott, that was really great. Finally, someone explained DTS in a way that's like understandable to a non-physical scientist. I have 2 questions. First one is, has anybody used DTS to understand the formation of moulins in glaciers? And the second question is, what kind of preparations did you guys go through in terms of like the teamwork that's required to work in an isolated extreme environment?
Okay, well, so the first question is moulins, and moulins are melted holes that water from the surface on a glacier runs into and then usually gets down to the bed, I think, right? And then can cause pretty significant melting at the bed and lubrication. Actually, one of our first users of this was a fellow from UC Berkeley who went up and was measuring stream temperatures in the water before it went into the moulins to look at energetics of these meltwater streams on glacial surfaces. Because it turns out the kinetic energy is quite significant. It causes actually some of the melting. So he was interested in that. Dropping it down into a moulin, yeah, that sounds really fun. We should try that. Maybe when they're not quite so running as much, maybe early in the season, drop it down, because I could imagine some dramas of the cable pulling you into the moulin, but I don't see why not. Yeah. The cables can be quite robust. I have a couple samples with me, and they also can be quite cheap. So if it breaks, we don't care, you know. But I think that would be fun. Yeah, that would be quite interesting. Again, in those situations, you know, think about it. Is there going to be much temperature difference? I don't know until you got way down into the bed. You know, most of it's going to be sort of at the freezing point. But that would be I know I have some people you could talk to who could work on, who have been interested in that. So yeah. And then as far as teamwork and whatnot, you know, we spent a lot of time on the phone. We were from disparate universities. We did meet once or twice. But pretty much the team that went down, the glaciologist and the oceanographer, had all worked in pretty remote, harsh environments before, and were just really good knowing what to do. So thing is, you bring like extra of everything. So, I mean, I had 2 DTS units with me in case one failed, and of course one did. And I'm on a satellite phone to the manufacturers in the UK saying, well, why isn't this working? Help me out. What does this error code mean? You know, anyway. So yeah, just prepare. That's all you can do.
Good. Other questions? Yeah.
Is there anything stopping using that same signal down existing fiber optic networks for phone or anything like that to record temperature through all the existing fiber networks?
So no, there's really nothing stopping us from that. In fact, the first application of this, the first demonstration was, that I know of anyway, was a group at École Polytechnique in Lausanne, Switzerland, where they used a telecom cable that was underneath the bed, underneath the crossing, Lake Geneva, Lake Léman, from Switzerland to France, and they shot a signal through it and were able to then measure the bed temperature of the lake. So I think that's the first. So no, there isn't. You know, you need access, and typically most optical fiber optic networks. You know, if you look at one of these cables that's here, that's a fiber optic cable. There might be 4 fibers in that cable. And there are slight differences in fibers, but for the most part, you could probably use them. You could use it, and for the most part, these cables are way over designed. So there's bandwidth, there's space on it that you would not be disrupting somebody's telecom network. So yeah, you could start looking at permafrost temperatures from telecom cables that are up in the far north without much difficulty. Yeah, I don't see any problem with doing that. I had another idea about doing that, but yeah, there's nothing is stopping from using that.
Scott, the cable in the water, I know your power requirements are an issue, but could you heat it and then look at currents below the ice? That's one thing I was wondering as I was looking at your project.
Yeah, so there's quite a few efforts now. Chadi Saidi at University of North Carolina, John Selker at Oregon State, a few others have been heating cables and then watching the dissipation of heat as a function of time, and that will tell you, you know, if a place on a cable is cooling off very quickly, then there must be some advective heat transport in addition to conductive heat transport in whatever fluid you're in. So yeah, there's lots of opportunities for measuring wind speed, and that's what Chadi's group has been doing really nicely, measuring the wind speed, wind fluctuations over very small, lightweight fibers so that they don't have any thermal mass. And in a water column, same thing. Heat it up. You can look at the dissipation.
Good.
Yeah, it's all a question of sort of thermal mass. If you have a really big cable, then it's going to respond more slowly to the environment around it. But literally, and I know folks who are doing this on balloons, you know, the fiber is 250 microns, so it's responding very quickly to the atmospheric temperatures. Yeah, it's sort of a fine wire thermometer, thermocouple.
Yeah. Good. Well, we're just a little over time. I think we might stop here and encourage everyone to come to Boffin's, where we can brainstorm on new uses of this cable. As you can probably tell, it's in its infancy. There are 1,000,001 uses that could pertain to many of your projects. You know, we could add rhodamine dye and do the Moulin Rouge project, maybe. What do you think about that? Anyway, I think beer will really help with brainstorming on these projects. So I want to thank again Scott for a really fascinating talk and for a great visit today on campus. Thanks, Scott.
Thank you. Thank you.